Hi guys. So let's start our seminar. Okay. Well, today I want to talk you about tokenizers. Tokenizers, some loss functions, and we just touched this topic in the previous seminar, but some sampling methods, some about temperature, top P, top K, etc., and some sampling generations in the large language models. Oh, it's just transformers. So let's begin with tokenizer because it's logical. We want to begin with this process, and it begins always when we put some prompt or query to the model. So first, what it has to do, so it's tokenize our sentence. How tokenization process can be. So in these really simple scheme, so we can see that first of all we can normalize. Yes, our text is just lowercase it. Then we can do just pre-tokenization. It's when we can separate our words, yes, and some symbols. Then we have our tokenization model, yes, tokenizer. Sometimes it, as you can see, some unknown symbols, unknown tokens, it replaced with special symbols. For example, as for like padding, for start of the sequence, end of sequence, it's special tokens, and it's in the next process like post-processing. So it's CLS token, yes, separate token, etc. So let's see how it works like just from scratch, yes, in our code. So of course, as you should know, we have like the basic word tokenization. It's when we just separate our text in words, yes, in some words, and then we can just take the lowercase it, yes, and we have our vocabulary. Then we can explain, we can produce for each word embedding representation. It's like embedding vector, and then we have vocabulary, yes, just a word, and it's embedding vector. So, and this is the simple tokenization. It's like we put it together, all these embeddings, yes, and put this vector with metrics to a large language model, just another neural network. So, but of course, we understand that we couldn't understand punctuation when we split in our white spaces. Yes, and of course, sometimes if in some cases there would be some out of vocabulary words, yes, unknown words, we couldn't preprocess it. So it's so these limitations really vital, and it's really hard to prepare a great model. Yes. So what we have in natural language processing to solve these problems. So first of all, I want to start with byte parent code, PPE. PPE is one of the, I think, most popular encoding tokenizers. So, and because first of all, this algorithm is really simple. We just produce it from scratch. So, and we see, you can see how it works. So, and Moreover, so of course it can handle out of vocabulary words, yes, and of course it's handles some punctuation. Well, I really recommend you to pay attention about these two links. So first link is about Stanford, really not so long Stanford lecture video. It's about 14 minutes about BP. So but if you don't have 14 minutes, I really recommend you to see Hugging Face explanation about BP. It's about 7 minutes. So here below, you can see the scheme from Hugging Face video, how it works, how BP works. I really want to play this video, so Hugging Face, to explain for understandable explanation how it works. Really simple, because in this scheme it's the final scheme with like a result, and sometimes it's really hard to understand how it works. So well, I think this is some ads, of course. Oh, another one about AI. So yes, well, byte pair encoding. So first of all, you can see some sentence or some text, yes, about what we want to tokenize and what we want to learn our tokenizer. So in this with this text. So first of all, we can count our words in it, yes, and make a corpus of words. So we can just count that in our text there are like two words like learning, two words learner, etc., and one word such as hugging face, hug, etc. So after that process, when we count our words, we just split every word, yes, in a char, yes, just, and then want to understand. So we have our vocab, yes, vocab, all chars, yes, all letters in these corpus of text with which we can understand the test, with which contains. So only these charts, not just letters, yes, in our vocab. So we have our vocab, but of course we understand that to encode each word with only with like just in each letter, it's really have operation first of all, and of course sometimes it's work not really accurately. So because of course you have some the variable length of the word. So and what do we want? We can count pairs frequencies in our splits. Splits in our splits, just each word we split, yes, and we just count our pairs. So and make these statistics, yes. So how many pairs from each other, yes, from each word, how many? So and then after this process, when we count all pairs, so as you can see, so some of them can repeat, for example, L and E, A and A, E and A, yes, but some of them really not so frequent, yes, just N and I. So we can sort these pairs in its frequencies. So, and can, for example, choose the most frequency pairs. And then we can combine it, just merge these two letters in one token. So, and then we merge it, yes, and we add this merged result, this merged token to our vocabulary. And now, if we see in any word these merge token, yes, with two letters together, yes, in one sentence, we just can replace it not in just two tokens from two letters, yes, but in one token, which represents the merged letters. So this is the core idea of byte-pair encoding. And now we can merge in all our splits, yes, these letters. So then we do the same process for every pairs, and we merge. Then we just yes count, yes, the second stage, yes, with these of course, as you can see, with these merged token, yes, and oh, well, we have another. We can choose another one, the frequencies, the most frequency token, yes, merged token, and then we just replace all in our splits. So, and then we repeat this process every time. Yes, of course, we add to a cab and etc. etc. So, and as you can see, so we can just count, then merge our tokens, add to vocabulary, replace our splits, and as you can see, we produce our splits from each separate letter to some tokens, to some lexems, to n-grams, but really sensible n-grams. So, and it's, of course, it's understandable better because in this process, yes, in these tokenizer, we can understand some similar words. For example, learning, learner, learners, and learn. Yes, just yes. And here we have some, just for example, we have some nouns, yes, like learner, and in multiple way, just learners, yes, mutual way. We have our gerund form, yes, learning, yes, and our just the core, just learn, yes. Okay, so and here we can replace it, yes, and we understand that all these four words is similar for each other because, for example, first token, yes, after tokenizing process, first token in all these words will be the same, and it's the core idea why it works great. So now we can work with it like more sensible process and more sensible way to understand words after tokenizing and words for model. So this is the simple idea of byte-pair tokenizer. I really recommend you to see standard detailed video about BP. It's not really the new idea, but maybe the explanation for, especially for you, will be preferable for this from this video. So, so we can, yes, we can produce these simple 4 steps in this algorithm now. Yes, and you understand what steps, what's each step like represent. Yes, split, first step, then count pair frequencies, merge most frequent pair, and then replace and repeat and add to vocabulary. So, of course, let's make this implementation of byte-pair encoding from scratch. So, of course, first of all, we have to normalize all our words in a sentence, yes, and of course, we normalize white space. So we have our corpus of text, this corpus of text, we will learn our BPE tokenizer for this text, yes. And as you can see in the future, so in the new text, sometimes which text don't have the same tokens, yes, some new tokens we have, can just replace it with unknown tokens. So when we separate, preprocess, of course, our this corpus in words, yes, and in char, so we have these initial vocabulary, yes, only for only with just letters in our corpus of text, yes, and it's only 24 letters. So well, this is our splits of the words, as you can see in the video. So our split text, etc. So all our words just in a white space with white space separately. So now we have to write two functions, only two functions. So it's pretty simple. First of all, merge tokens. So merge tokens, when we give the pair of tokens, yes, to this function, maybe corpus in, it's our corpus of text, yes, we will find there our pair, yes, and then we replace it. So, well, we make our bigram, yes, so, and we just replace our pair, yes, with words. So in corpus text, no text, and then we just add to our corpus this new word to our vocabulary, yes, and then we return it. So this function merge tokens and place it in our vocabulary. So great. So and the main function is learning byte pair encoding. So this function, of course, tokenized our corpus. It's first of all, then make vocab, yes, and then we go for a non-merges. It's how many merges we want to make. Of course, if we make the really great high number of mergers, we can provide just word and word tokens, yes, without separate, because so it's how many. If we make less, pretty less this number of mergers, yes, so we can just replace only some pairs, some really frequently, but pairs. And then we had some tokens just in one letter. So we will see it in our experiments. So, but now merges, it's really hyperparameter of our text. So in our merges, yes, we have a cycle. Cycle, what it is? So we have our pairs, yes, and then we in tokenized corpus we just compute and count our frequencies of pairs, yes, about 2 tokens, 2 nearby tokens. It's vital nearby tokens, yes. Then we choose our best pair, it's the maximum of our pairs, yes, just frequency of pairs, yes. Then we merge it, yes, we append it to the best pair to our merges vocabulary, yes, and then we add it to vocabulary. So it's this is these 2 letters, yes, and then we tokenized our corpus. We launched our function merge tokens, which was here. So that's all. That's really pretty simple. It's more simple. This code more simple as the next one about word piece tokenizer. So let's see how it works. So we can produce 50 num merges. So and so here it is. Yes, our learned merges is just char, characters. It's some NT pair, yes, etc. frequencies. And well, let's print our new vocabulary, yes, and produce our function BPA encode. Yes, it's when now our vocabulary size is 74, more than 24, of course, because we add our 15 new words. Yes, and we have these tokens now. Yes, let's encode our text addresses adjacent. Yes, and okay, great. I think it's great choice. So if we want to make, for example, more merges, for example, 100, yes, and make it some, I want to insert yes, I think replace this. Well, we want to make our 100 merges additionally. So so it produce in a final way, we will have 124 merged pairs. So in our vocabulary. So here it is, and our vocabulary size it's 92. Okay, well, I missed in some anyway. Well, let's. Okay, this is what I just told you. When we want, when we did these num merges, pretty large, yes, for example, 100, we learned all our words. So in merged vocabulary. So this is why when we make our sentence, we just separate, we encode our sentence just with white spaces and our words. That's all. And this is not really great sometimes, because why we why we have to learn so such complex way to learn BPA encoders, to learn it, then encode, but we just can make so just dot, split, yes, and in a white space. That's all. And we produce the same result as we did it in the beginning of our seminar here. Yes. So nothing special. We can just add our white space, etc. So that's all. This is why we have to understand that num merges. It's really a vital parameter, and we have to understand what really we want. So, and how many merges, how many vocabulary size, which vocabulary size we want to make. Of course, it depends of our corpus of text. I mean this one. So if you have the larger corpus you have, the bigger, the more, of course, the larger num merges have to be. But of course, it's just a practice, and of course, you have to understand that maybe you can vary. You can make some list of hyperparameters, yes, and choose the best. So let's move to another tokenizer. Another tokenizer is word piece. It's the same. It's work the same based on the same idea as BP tokenizer, byte pair encoding. But in when we produce our frequencies, yes, the frequency value of our pairs, here we don't do so. Here we have some word piece here is like based on probabilities, and some probabilistic approach to build our vocabulary. For example, you can see in this picture, yes, we have the probability of the frequency of our pairs, about 2 tokens in a just nearby, I mean, and token probability separately for 1 token and for 2nd token. Then we just count this probability for each tokens, for each letters, I mean, yes, for each tokens. First of all, of course, it's letters, yes, like chars, but then we combine, and then we produce like a token, then we want to compute, etc. Yes, some other letters. So, but of course, from 2 tokens. Yes, and so that is one difference from byte pair encoding. So only in that. So we have probabilistic approach. We produced some probability of each token, and with each with the nearby situation, and then we compute our result. That's all. Then we, of course, sort it. We choose the most frequent, the most probabilistic, yes, variant with 2 tokens. We merge it. We add it to vocabulary. We just replace it in our splits, in our corpus of ports, and then we repeat the process. That's all. So that's pretty simple. And of course, here, this approach, word piece, it's used in BERT models and BERT family. Yes, it's like Roberta, Albert, etc. Some other BERTs. Yes, so you can see it in a transformer library. So, and what's great unit that here we can add special suffix. For example, to just I forgot how to what's this. So 2 special symbols. Yes, in unknown units, in unknown tokens. So, and here we can see the implementation of this word piece tokenizer from scratch. So it's implemented like in a class way. So because we have some methods, and it's pretty easy to make it in a class. So first of all, we have some unknown tokens, but it's just initializing of the class. It's we can initialize some our parameters. Yes. So well, learned vocab. So this is the main function as the learned BPE, the learned vocab. So this is here we of course have the same parameter. Yes, like vocabulary size. Yes, it's what we. It's like num merges. Yes, it's which size of vocabulary we want to take. Of course, 100 it's pretty great number for our examples. I think 100 it's enough. So and so as you can see, we add in our vocabulary some special tokens like a pad, unknown tokens. Yes, CLS. It's like from the beginning of the sentence. So separate token and mask. Mask, it's sometimes it's pretty vital token for learn BERT models. So it's we have a masking. If you know, you know. So we have a masking a token in inside transformer BERT, and BERT. BERT has to predict this masked token and to choose it correctly. So it's how it learn. So yes, we convert all our tokens in a lower case, then count our words. Yes, and add in our vocabulary all our char, yes, just letters, for example, yes. Then we have our cycle in vocabulary size, yes. We just count our pairs, then we split it, yes, and it's the function, here it is. It's split word in subwords, yes, based on the vocabulary. So it's work pretty easy, yes. It's we have the our word, yes, and then if we don't know our substring or our tokens, yes, we just replace it with this unknown token. So yes, and then but in the other way we just make it, that's all. So and then we decrease our line of code. Yes, it's just the itemize. So that's all. So if we don't have our current subwords, we just add some prefix, and that's all. So and we return these subwords. Yes, so it's the list of our. So that's what we do here. Yes, we separate it, like split it, our word in our subwords based on vocabulary. Yes, and then we just produce our pairs based on these subwords. This is a subwords like token. Yes, and then we count it. Yes, and then we can choose the best pair, the most frequent pair. Yes, and then we just produce it like just our tokens. Yes, then we can connect it and add it to vocabulary. That's all. So and okay, so that's all. Yes, and tokenize process is pretty simple. Yes, we have our text here, and we just lowercase it. Yes, it's like pre-processing. Then we tokenize it. Yes, in a subwords, and then we returns our tokens, the list of tokens. So yes, let's see how it works in a small example. Yes, we have our corpus of text, hello world. I think we can just did so, but it doesn't matter. We lowercase our shift text. So, and that's all. Yes, let's learn it. We can take our vocabulary size in 40, and you can see that we have a padding token. Yes, like some CLS, masked sometimes. Yes, separate, and that's all. So, and here we have these tokens: word, hell, yes, word piece, word p, etc. So, and this is a new test. And as you can see, here we learned our vocabulary, yes, our vocabulary size now it's 40. And now we have new text. As you can see, we have some new words. It's a new word. So let's take it. So our tokens for this text is absolutely correct, but we had a new word, like a new, yes, and this was replaced by a known token. Okay, so this is the best way to learn some large language models or some transformers, yes, to use it and to learn it based on the any corpus of text. You have just set the vocabulary size. For example, we can repeat our learn of a word piece on our corpus text, and then repeat our experiment. I think here you can see that sometimes it can add some special symbols. Yes, this is why this example is more in text and more in characters. Which is why we added. So and now we can see that we have a lot of unknown tokens. That's of course because that's obvious because we don't have hello token. Yes, hello words. We don't have word no word in this text, no corpus of text. Yes, and some text, etc. But if you add some special words, yes, size, not. No, I think because these 40 vocabulary size is pretty small for such text. We can just add 100, and of course, so as you can see, so size is okay. So we detected. So that is how this hyperparameter, like a number of merges in the previous example. Yes, we of course, as you can see, how vital it is, how vital to produce, yes, to choose the accurately vocabulary size for your tokenization. So, but if we make just a lot of I want just add these example here, but without new test and maybe without maybe some not really clear words. Yes, I think that's enough. 100. So yes, as you can see, so we just replace it. We didn't know the exactly word. I think it's because we make our corpus of text bigger, but we didn't increase our vocabulary size. For example, if we can increase it just in 20, yes, everything is will be okay. So this is one more time why vocabulary size, this parameter, this hyperparameter, it's pretty significant for tokenization process. So you can sometimes you can get just weird results, bad results of tokenization. Pay your attention of vocabulary size first of all, because sometimes you can choose just the lower vocabulary size or a bigger, for example. Yes, if we did here 200, for example, I think it's, of course, we just separate all our words, yes, without unknown tokens. That's all. If we have our all our words here, yes, so that is that it is like split in a white space. So that is why pay attention of the corpus of text, pay attention of vocabulary size, pay attention of the tokenized text. So this was the first part of our seminar. It was one of the biggest parts. So it's the start process of your working with your model. Yes, it's like tokenization. Then we go to train, but we will not train our model. We just talk about losses. So we have a lot of losses in machine learning, as you can maybe know, as you already know. I want to explain you which just show you in an example these losses, yes, and explain what type of loss we have implement in what cases. So let's begin with, I think, one of the frequently, I think, loss, it's cross-entropy loss. maybe log loss, as you can heard it just in this type. Yes, and it measures the difference between two probability distribution. Maybe you can say that, hey, Kullback-Leibler distribution, Kullback-Leibler score, yes, make the same. Yes, of course, it's Kullback-Leibler and the cross-entropy loss make the difference between two probability distribution. But cross-entropy loss predict the probability distribution. So it's like the true, it's over classes. Just we predict the probability distribution over classes. For example, text classification, yes, spam or not spam, yes. It's the NLP, natural language processes, like a task, like an error, like a scientific error, yes, like industrial error too. It began from these simple tasks. So it was at the ending of the 20th century. So this is the email, so the .coms, yes, the .coms crisis, maybe you heard about it. So, and before it, so humanity just created emails, yes, and this email, and first emails like Gmail or some another, just Yahoo or something like that. So it was so long years ago. So there's they in the 19th there was nothing spam filters. Anybody nobody knew how just do just yes, and why they needed. Yes, but after some cases, as some cases like when many users can got a lot of letters with a spam, with some ads, with some, I don't know, just another rude words. So of course, scientists they thought they got this task, yes, to make spam filter. How we can recognize from a not spam letter and spam letter, just normal letter from your colleague, from your friend, from your mom, I don't know, yes, and from your from just organization with ads, organization from some, I don't know, rural, yes, or rude words, so, or maybe it's can be some crime, etc. So and the cross entropy loss, that is the loss which can classify these tasks. Yes, these classify these two classes. Yes, and of course now how it works now, we use it in a training process of large language model. So we just cross-entropy loss, it's like we can just produce the probabilities of token, yes, at the end of the layer of large language models. And then we can take the most probability token and put it in our output for our user. And then we repeat this process many steps. So this is here it looks like, yes. We have our probability and log of our probability, yes. This is our entropy. And of course, sometimes we use it for uncertainty in our model prediction, but yes, and some active learning. Yes, so how it's compute, so you can see, I provide you examples. So calculate entropy, so it's pretty simple, honest and sum, and we have our probabilities. So it's like one probability, but so one is the original, and then with under logarithm. So, this is the binary distribution. Yes, we have 0.5, yes, 0.5, and then we calculate our entropy. So, as you can see, our entropy is a bit 0.7. So, visualization. This is the great visualization of our entropy binary distribution. It's commonly used in, if you know, it's commonly used in random forest. So, what it is in random forest, if you see, so I want to say that this is the maximum of our output of binary distribution. So why it's the maximum? So if you remember about random forest classifier, then we have some splits in our probability. Yes, for example, split our some color balls from red and green. So, and when we split in cross entropy or entropy of this binary distribution, yes, it's like a function, like a metric, yes, to grade split. So, and if you have, we want to minimize it, yes, as you can see, the minimizing the entropy, we go to 0 or to 1, yes, and this is what happens if we minimize the splitting in our distribution. Yes, if we have red balls less, pretty less, yes, much more less than green balls, for example, yes, we go for here to 0, for example, yes. But if we have more red balls and much more less green, we go to the 1. But anywhere in these all these two examples, yes, we minimize our entropy and we did a great split. So why in one case the 0, in the second case it's the 1? Yes, first 1, because it's just the binary problem. We said that red balls, for example, it's the 1, and the green balls it's the 0, and we won't recognize it, just recognize. And when we see a lot of red balls in our split, yes, we can recognize by our distribution. Yes, for example, we can count our frequencies of our red balls in our split, in our set. Yes, and the more red balls we have, the lowest entropy will be, and the entropy in our x axis, yes, it will be 1. At the same time, if we do the same process and the green balls, we got 0. That's all. We can just change the colors of our balls, and we can change the numbers, but nothing changes in mathematical setup. So I think it's clear. So if you have some questions, so we can move to the topic of our random forest and explain it. But I just provide you some information, an example, how significant this cross-entropy loss is. So we use it in our classification task. We use it in our trainable process of large language models like GPT models. We use it in random forests, etc. So it's really vital. So go ahead, and we have our KL divergence. So when I see KL, I just thought about Kuala Lumpur city, but KL is Kulbak labor divergence. Yes, and this divergence measures how one probability distribution diverges from reference distribution. That's all. So this is looks like this formula. Yes, we have our distribution like Q and P. That's all, and then we something the same like cross entropy. So, and it use Kullback-Leibler divergence. Yes, it used in sometimes in fine tuning of large language model, sometimes in alignment, especially reinforcement learning. Yes, it's like RL, so it's reinforcement learning based on human feedback. So sometimes we use it in DPO. It's something else. So and variation autoencoders too. So so you can see. So I think it's pretty simple formula, and here we have the example. So we have 1 over distribution and another. This is the reference, yes, of our. This is the reference P and the Q, and we want to understand how Q distribution differences from our P distribution. That's all. If we put here, for example, you can see, so our value increased. So if you put here, for example, 35, it's increased. So here, yes, it's decreased. I'm sorry. Yes, it's decreased. Yes, if it decreases, so it's great. So I just missed the numbers. I'm sorry. So I think you understand. Well, and here it is. Here the graph of Kullback-Leibler probability. Yes, and here it is. Well, so cross-entropy loss and Kullback-Leibler divergence. So sometimes we just combine it, but in some way it's really necessary. Yes, if we want to see some two metrics, we can just in some cases we can weight it. Yes, we can put the weight to Kullback-Leibler distribution and cross-entropy distribution, and it works. Of course, it works great. So binary cross entropy loss. So it's pretty simple. So because it's just these formulas. So if you can see, it's the same formula which we saw some previous examples, but in just in binary case. Yes, as I said, so spam detection, sentiment analysis, positive, negative labels, yes, some classification signals, etc. So so just a great example. So you can see how the prediction, yes, for example, target this prediction differences from the target are true. If we did here the same values. Oh, none. I'm sorry. Yes. So I forgot to see, but I think it's make less than it was. Yes. Yes, absolutely. Yes. So the less our loss is, the better our trainable process goes. So multi-label cross entropy loss, I think it's the same distribution, just we just did some model prediction, so multiple cases, multiple labels, that's all. So and the same formula like in the previous one example, just in some multiple variants. So and we can here use our cross entropy loss from a torch. And the last one, I think one of the, I think two in which create in some trainable process of neural networks, recommendation systems, especially recommendation systems. So it triplet loss. So it's comparison, it's comparing an anchor and a positive sample. similar to anchor, and the negative sample dissimilar to anchor. So I think we can it's the name of sometimes constraintive laws, and I want to so yes, constraintive laws, and here I had the great image with okay, with dogs. I think this, but not really. I don't really sure. Yes, sometimes it's producing face recognition, of course. Well, okay, okay. Um, no, 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 constraintive loss. Function, or triplet loss. Yeah. So, well, yes, in these simple, I didn't find the image, yes, but in this simple process, as you can see, if we have our embedding space, yes, vectorizing space, and we not learnable, for example, initial, yes, and we there have some anchor. For example, it can be embedding of our images, and we have an anchor of somebody, and we want to make the similar people in face with the similar faces near near to this anchor, and not the of course other people make a, like a go away. So in our space, yes, on the long distance. So it is triplet loss. It's did it. So it's because it's produced. So it's combined, not combined, just make our anchor and the positive class like in a short distance in our space after learning. So well, it's sometimes this is the formula. So, and we minimize distance between anchor and the positive, and maximizing the distance between anchor and the negative sample. So, and of course, we did it some recommendation systems. Of course, it's when you have items. Yes, when you have, for example, from production task, you have an embedding of our user with some SOSDEM features, for example, age, some sex, some salary, region, yes, the job, etc. Maybe some about his family. And so you have this embedding of user, and you have many embeddings of items. For example, in some large company, one large company in Russia, in e-commerce, yes, there were so 150 millions embeddings items in a market. So it's a huge vocabulary. It's a huge data. So, and you have just approximate number of items, and of course you couldn't recommend all these items for a person, for a user. Yes, you have to choose for example the thousand items from all of these which fit the best way with this user. And how we can solve it? We can solve it with some B encoder. For example, you can see like the cross encoder. We can use it with transformer models, and we use our constraintive laws or triplet laws in our learnable process, in our training process. Yes, and it's another topic how we prepare our training and target data sets for these tasks, but just believe me, it's a complex it's a complex task. Yes, and so you can put these trainable training data set. Yes, you have the embedding of our user. You have some embedding of items which he bought in his history. Yes, of purchases. Yes, he purchased some items, and you can see this history. Yes, maybe you can see some greatest items. Yes, in his account, but for example, just in history. And based on this information, you have minimized the distance with the relevance items for this user, and maximize distance for other items. And you have to recommend the thousand of the best fit with the best fitting items for this user. And this model, it's this task is a R&D task, and it's pretty hard, and it's really challenge sometimes, because it's you have the cold start problem. For example, just yes, if you if you think, oh, it's so simple, we have our data sets, yes, and that's all. Yes, and what won't you do with the new users, yes, which don't have this history? He has only this embedding, user embedding, and this is there are a lot of users with such features. So only embedding with SOTSDEM features, and that's all, without history, or history in 1, 2, or 3 items. That's all. So it's about 60-70% of all users. It's these users. So without purchasing anywhere, or purchased 1, 2, 3, maximum 5 items. That's all in a whole time. So, and of course, it's a pretty hard task, but triplet laws and the constraintive laws used there. So, and used there. Well, yes, our that's all about losses in NLP and some model tasks. Yes, I want to move the last topic of our seminar and make to some introduction. Yes, I did it in the previous seminar, but more first of all. So I want to make a text generation parameters, yes, and explain you maybe twice, maybe one more time, about temperature, about top key parameters, top P parameters, some greedy search, etc. So, but before starting, I want to ask you some questions about the first 2 topics, about tokenizers and losses. If you have them, so you can ask me now, and I can just make some pause. So. So don't hesitate to ask some questions about material. So it's okay. You can you can just chat it, or just ask with voice as you want. Well, 3 to 1. If you don't have any questions, so let's move to this last topic. And here you can see some of the scheme of generated our transformer. For example, we have decoder only transformer. Yes, it's start here. It produce some vectors, output vectors. Yes, then we have the linear left, softmax, token probabilities. So here, that's all. Token probabilities. It's the end of a model. You just generate by softmax. Softmax is the cross entropy, something else. Yes, some of the function. Yes, and here we can choose, for example, in the simplest way, we can choose the most probability, the highest value of probability token, then put it in our output, yes, for user, and then to repeat the process. That's all. But of course, this is simple, just choosing the tokens. It's work not really great. For example, you have some tokens which don't fit pretty well, and now you have, or your model doesn't sure about the next token, and it's don't have just like these high probability of one token. It's make the there's approximately equal probabilities of two tokens. Yes, and just its difference just in, I don't know, in some small value, for example. This is why you have to choose both of them and make the maybe some beam search. Yes, you can provide some to see some these sequences. Yes, two sequences of two process of generating. Yes, and then choose the most great value, because sometimes in one stream, in one of these two streams, or many streams, yes, for example 5, you will have pretty more value of probability. So then you can choose the stream. But this is greedy decoding. Yes, this is that's when you choose the token this with a high probability. Yes, and input text, then tokenize text, and then we process this repeat our process. So let's see the temperature. As I told you on the previous seminar, the temperature is just we just divide the logit of our token, if you remember. So we varied this temperature in the previous seminar, yes, and we could see so that our generation from neural network. So it's of course it's varied too. So, and we saw the probabilities, the variance of our probabilities, logits. So the output. So, and as you can see, if we divide in a low temperature, we have a high probability. So we, in our way, we increase the probabilities, yes, the probability of one token. So we just squeeze our distribution probabilities, yes, and we separate this one token with the highest probabilities, and other tokens have the lowest probability, much more low probabilities as this one. So, but these make so the creation of our model. So it just produce only the highest probability, and that's all. Yes, but if you make the temperature higher, yes, your probability just make wider. So, and you can choose in some words. So you can choose this one or another, or as I've told you, so you have just two tokens with the approximately same probabilities. Yes, for example. This is what temperature does, and I really hope so you remember it, so and you can learn it. So, and let's see some practice. I don't want to start the code really because it's already I already did it. So, and sometimes it can be in some process we will work with large language models. It can be so in some can providing really long time to see the result. Yes. So, and we have a GPT-2 model. Yes. And here we generate, we make our some, for example, here we have three variants of our temperature. Yes. And we we just wrote this function. Yes. Generate with the temperature. Yes. And here we see our prompt. Yes. The future of artificial intelligence is, and the model have to continue this sentence. Yes. So here it is. Temperature 0.2. It's the low temperature. So and here it is. The future of artificial intelligence is not yet clear, but it is clear that the future of artificial intelligence is not yet clear, but it's clear that the future, etc. As you can see, the model, did some cycle in generation, but it's not the cycle. We just provide it some tokens. The future of artificial intelligence is, and it, based on these tokens, tried to generate another, but with the lowest temperature, the highest probability of the continuing token is that this token which is in our sentence. So it is this is the rule of transformer. So another example, if we have our temperature 0.7, it's the normal temperature. I think it's the average temperature when you generate some prompt in your large language models, when you code with it. So it's all right. So the future of artificial intelligence is also uncertain. If artificial intelligence is good enough, what about machine learning? AI may not be nearly as good as the human brain, etc. So as you can see, the output is really sensible and understandable. So with a nice, with a okay, usually pods, and it looks like just the Wikipedia just site, yes. So it's okay. But if what we is the next example and the last one, we have our temperature really great. So not really great. The greatest temperature is the 2.0, but 1.2 it's the really great temperature. So the future of artificial intelligence is going to need some really big changes, just like smart, collaborative, and open world AI, not a lot of real human inventions. So the past 100 years, maybe decade, new technologies, new forms of, etc. So as you can see, we and we already seen it in our previous seminar. So the higher temperature is, the more new tokens in our output are. So, and this is what temperature do. So in the example, how it works. So I think you really remember it, and I think learn maybe. Let's move to the, I think one of the latest topics of our seminar. So decoding strategy. So decoding strategy, we've already told it in our previous seminar, but okay, we have, for example, we have 4 different decoding strategies in this seminar. Of course, we have more in our science, in our industry, but in the seminar we just can see just 4. Greedy search. Greedy search is when you choose the highest probability. Beam search. As you can see, we explore multiple sequences, yes, and keeping the top 4 most likely sequences. Top K sampling, it's like samples the next token from the top 50 most likely tokens. Yes, so I think it's we just did it in our previous seminar. So and top P sampling, it samples the next token from the smallest set of tokens whose cumulative probability exceeds 0.9. So okay, here it is. Here are our strategies, and compare machine learning workshops help people. Greedy help people learn how to use the internet to solve problems. I think it's not really obvious because our sentence was about machine learning, not the internet. The workshop is open to anyone who wants the workshop, and then we cycle. Okay. So beam search for beams. Yes, machine learning workshop help people how to use machine learning to solve real world problems. We see here really sensible sentence. Yes, in this workshop, you'll learn how to use machine learning to solve real world problems. Yes, it is. And learn how to use, okay, and then we just generate something else. Top K. Machine learning workshop helps people to improve when they learn to speak with greater clarity, solve problem faster, maybe. And top P, machine learning help people create and implement deep learning model. Yes, of course, that will eventually learn their business applications. Why not? So as you can see, it's just example which helps to understand how it looks like. Okay. I provided you some links in our chat when you this site, yes, with just images, yes, where you can just vary these parameters and see the generation. So, and see the distributions, of course, too. So the probability. So, and the last one topic in the temperature and entropy visualization. So let's visualize and analyze the effect of our temperature. Yes, move back to our temperature, and the entropy of language model prediction of given prompt. So how changing the temperature parameter so affect the entropy, so uncertainty, the model's predictions. So and here you can see that the highest temperature is, the highest entropy is. So that's pretty simple. The highest our probability, the highest our probability output. That's why we have so many varying, so many randomless text if we have a great temperature. But the highest value of our temperature, it's not really great, it's not really good for the inference or for testing our model, because of course if the highest temperature is, the more hallucinations can generate our large language model. So it's pay attention to it. The lowest temperature, it's not pretty great too, because as you can it can cycle in it, yes, and cycle itself, and provide not really quality result. So we have find a balance between our temperature, all these other parameters, top key, top P, etc. So that's all for today. This was really rich seminar, so I really appreciate you to visit it, to see it. If you have some questions now, don't hesitate to ask me. So, but now let's end in our seminar, in our practice work. 3, 2, 1. Okay, if you don't have any questions, so thank you very much for this seminar, yes, for visiting it. So goodbye, have a nice week.
Thanks for the lecture.
Recording, yes, goodbye, guys.
Goodbye.